orthogonal curvilinear coordinates. The basic equations of fluid dynamics are valid for any coordinate system. We have previously expressed these equations in terms of a Cartesian coordinate system. For many applications, it is more convenient to use a different orthogonal coordinate system. Let us define theta 1, theta 2, theta 3 to be a set of generalized orthogonal curvilinear coordinates whose origin is at point P, and let G1, G2, G3 to be the corresponding unit vectors. See figure 1.2. The rectangular Cartesian coordinates are related to the generalized curvilinear coordinates by the following expressions. X is a function of zeta coordinates, y and z also. Using Einstein notation, we have the following expression. So, if Jacobian is non-zero, then we have the following expression. Theta can be expressed by x1, x2, x3. The elementary arc length ds in Cartesian coordinates is obtained from the following expression. If equation 1.68 is differentiated, the following result is obtained. Where the following formula is true. This G J I is the ith component of vector G J in Cartesian coordinates x1, x2, x3, so that we have the following expression. Scalar product of basic vectors equals the following expression. For an orthogonal curvilinear coordinates, we have the following. The scalar product of two vectors is equal to 0 if j is not equal to k. So we have the following formula. If equation 1.71 is substituted into equation 170, the following result is obtained. Sorry. Where h1, h2 and h3 are defined by these formulas using the derivatives of x, y, and z. The above formulas can now be used to derive the fluid dynamic equations in any orthogonal curvilinear coordinate system. Examples include the following. Cartesian coordinates. Z1 is equal to x, Z2 is equal to y, Z3 is equal to z. And we have the following expressions for h and u. Cylindrical coordinates. Z1 is equal to r, radius, Z2 equals theta, and Z3 is again equal to z. Then spherical coordinates. Z1 equals r, Z2 equals theta, and Z3 equals phi. And we have the following expressions for h and u. Then two-dimensional 2D or axisymmetric body intrinsic coordinates. For them we have got the following expressions. Look at the picture. Here k of xi is the local body curvature, r of xi is the cylindrical radius, and m equals 0 for plane 2D flow and 1 for axisymmetric flow. Now we will give the main equations in a cylindrical system of coordinates, as in example. The continuity equation. Three momentum equations for u are for u theta, and for u z. And the last equation is energy equation in this coordinate system. The expressions for stress are given by the following formula: tau rr, tau theta theta, and so on. Here are the expressions for heat fluxes qr, q theta, and qz. The forces, the f functions, are given by this expression.